Good morning. Welcome to Turfgrass Epistemology. I'm TravisShaddox. I hope everybody's doing well. It is a very bright, sunny, cool day in Lexington, Kentucky. It's March 12th, 2024. It's going to be a good day. It's been a very odd winter, kind of dreary and wet. But hopefully it's sunny. It was sunny yesterday, cold. It's going to warm up. I think it's going to get into the 60s, high 60s today. Yeah, I think it's going to get in 70 tomorrow, I believe. So, yeah, it's 46 right now, but it's going to get up into 66 today. And then 70s in a couple more days. So, it's spring. There's a lot of trees changing up there today. And saw some POA annua going crazy. The last 2 or 3 days, I saw a lot of POA out there growing. So, things are changing, and it's that time of year where we're about to get going. So it's nice. I'm TravisShaddox. Welcome. Hope everybody's doing well. We're going to talk about potassium today. Bit of a challenging paper, but we'll get through it. Gray, good morning. CVO Hobo. Welcome to you. Sounds like a new handle to me. I haven't heard that before. You say, good morning. I found this channel over the weekend and I have learned so much that I have been doing wrong. Okay. Thank you for sharing your wealth of information. Well, you're welcome. If you go back and look, there's several times throughout the past episodes where I've tried to provide some clarity on how I feel the content is, and that is, it's not me saying these things. It's not TravisShaddox saying these things. I'm just doing my best to communicate the scientific literature in a way that you all can apply it. So there are some times where I do opine, for sure. I think most of the normal, regular listeners can tell when I'm just giving my opinion versus, just communicating the literature that I'm going over. But I do appreciate it. But I just want to make sure that that's clear that, this is my area of specialty. I'm an expert in these areas of nutrition and soils, but a lot of this stuff I go over, I've been reading for 20 years, but I still go over it. It's not my work. I'm just reviewing what was already published by other authors. Sometimes it's my own work, but most of the time it's not. Andrew Burris, good morning. It's full sun in southeast North Carolina. 70, nice. My family, when we came over from Europe, landed in North Carolina. We have the boat documents where they signed when they landed in, can't remember exactly what county, but there's a couple places in North Carolina that are called like Shaddox Creek, and that's where my originally family came from, England, I think it was. Landed in North Carolina. Turf Nerd Lawn Care, good morning. Connecticut Cubonican. Mid-60s in Connecticut. Rhodiamine and zero soil test on my home lawn maintenance agenda. Okay. Okay. Yeah, it seems a little early. I went out with some prodiamine a couple days ago, whatever it was. It seemed awful early to me. But it had been 60s and 70s for several days in a row. The soil temperatures are already like right at the, low 50s already here in Lexington. So I had a day where I had some time to do it. So I went ahead and did some of that too. Randy, good morning. Brady, Lush, Super TA, Mitch, Transition Zone. Good morning to everybody. So we only have one article today. It is... it's an older article. There's nothing wrong with older articles, but it's a little bit challenging to go through. And there's some information in here that is antiquated, and I'll explain that as I go through. But before we get to that, what I want to do is put up the scoreboard. So we're going over potassium, and here's the scoreboard for Turfgrass response to applied potassium. We've gone over many potassium papers in the past, but this month, seems like I've gone over more than 3 papers. But this month, so far, I have 3 papers on the scoreboard. And so what I'm looking at is a scoreboard with turfgrass response to applied potassium, where I have a positive column where the literature concluded there was a positive response. I have a none column, and I have a negative column. So the negative column where there was actually a harmful effect of the potassium, none and positive. And then I had the initial soil test K. That's really for me, but for you all to know too if you want to know it. And then the turfgrass that was used. So right now we have the Fitzpatrick and Gallard paper concluded there were no responses to potassium. And in the same paper, they concluded there was a negative response to potassium in some cases. But they didn't conclude that potassium had any beneficial response. And that was on Kentucky bluegrass with a modified Morgan extract of 75 parts per million. Ebden and his team up in the Northeast concluded there was mostly no response to potassium. Then there were some negative responses to potassium, but there was one positive response to potassium when the potassium was applied with nitrogen at 7 pounds a N on perennial ryegrass, which again, I don't think we would normally do that. But when potassium was applied with nitrogen less than 7 pounds, there was no positive response. But I put that in the positive column because there was one little area where there was a positive yield response. So the growth increased when it was applied with 7 pounds of nitrogen, but not with less than 7 pounds of nitrogen. So I would mark that as a questionable positive response, but nevertheless, it was in the positive column. And that was with a Morgan extract of 119 parts per million. And then yesterday's paper was the Johnson 2003 paper with creeping bentgrass in Utah, where they used Olson, and the potassium level was 16 parts per million. And they didn't report any positive response to potassium. Most of the time they reported it was no response. And then in the same paper, there was a negative response. And if I recall, that was due to the phytotoxicity of the potassium application that actually burned the grass. Today, we're going to go over a paper that uses ammonium acetate at 15 parts per million. This is an older paper in the 70s. So at that time, there wasn't the soil tests that we use today weren't quite as prevalent, like the Malix and so forth. And it's on creeping bentgrass. And there were some positive responses in this paper, but before we get there, I'll go over the paper. Okay, so that's the scoreboard. We have 1 in the positive column, 3 in the none column, and 3 in the negative column. Okay. If I had a crystal ball or some sort of time machine or something, I'd want to know how it got to this point in turfgrass management with potassium. Someone's got to know. Someone's still got to be alive that can tell me, how did we get to the point where we're applying so much potassium if the majority of the literature shows there's no responses to potassium or negative responses to potassium? Occasionally, there'll be positive responses to potassium, as I will eventually get to with winter kill. There's clearly evidence to support the application of potassium on low K soils whenever winter kill will likely occur. We'll get there. But there's so much in the literature about no responses. Nothing happens. Or there's a burn. Or there's a reduction in quality, or a reduction in density, or whatever. Or there's an increase in disease when you apply potassium compared to if you don't apply any. So if I had a crystal ball, or I had some way of knowing, like if there was some way to know, how do we get to this point? I'd like to know that. It's just bizarre to me. So that's my preamble. Let's get into the article, because it is a bit challenging. Every now and then we run into one of these articles that is, there's nothing wrong with the data per se. It's just it's just challenging to read through the way it's formatted. The article is entitled "Effect of Nitrogen Source, Potassium Source, and Potassium Rate on Soil Nutrient Levels and the Growth and Elemental Composition of Pen-Cross Creeping Bentgrass" by Waddington, Moberg, and Deutsch. I don't know how to pronounce that word. This was published in Agronomy Journal in 1972. So what we're going to find in this paper is there's one or two. I don't want to say it this way because Waddington was a really good researcher and they did a lot of really good work, but I just want to be careful so someone not to misinterpret this, is that there's one or two sentences and paragraphs in here that are not true. But back then in the 70s, it was almost considered common knowledge or general knowledge. But since then, there's been so much work done that we've determined that it's not true. So it's not really the author's fault per se. But I wanted to use it as an example to make sure everybody understands is that when something is in the literature, the scientific literature, in Agronomy Journal, which is a top-tier journal, it doesn't mean that it's true. Oh, it's in Agronomy Journal, therefore it must be true. It's in Crop Science, it must be true. Okay, there's just a much greater probability that we should have confidence in the information than not. But it can still be eventually determined to be not true. Okay. And that's what we'll find in this paper a little bit. There's only one or two things like that in here. But more importantly, the challenges I find with this paper is that they report data in the way similar to what other authors did in the 70s, where they look at like frequency of differences rather than showing turf quality reductions or turf quality increases in response to potassium. They'll just say the number of times that it did differ. And I was reading this article and they show some positive responses, or they indicate there's a response. They just say there's a difference, so there's a response to applying potassium than when not. And I'm like, well, that's curious because you don't see that a whole lot, And then as I kept reading through it, they have a sentence or a paragraph in there. I'm like, oh, okay, that's what happened. So stay tuned. We'll get to it. All right, here we go. So the relationships between soil nutrients, applied fertilizer, and turfgrass response are important in planning fertilizer programs for turfgrass areas. Nutrient levels and balances of plant nutrients not only influence turfgrass growth and color, but also have been shown to influence turfgrass tolerance to both high and low temperatures, incidence of turfgrass diseases, invasion of weed species, and recovery following injury from these and other causes. So right here, you can kind of infer what I'm saying when I say there's some information here that's antiquated and just not true at the moment, not true. When he says nutrient levels and balance of plant nutrients. Man, hang on one second here. My ink color is all screwed up lately. So the balance of plant nutrients is what is used by charlatans in our industry to convince you to buy their products. And they're things like base count and saturation. They'll say, well, your calcium's too low or your calcium's too high compared to magnesium. Or your magnesium's too low, so you got to apply, magnesium, or magnesium's too high, so you got to apply calcium. And you should have a great deal of confidence that when you're speaking to someone who's telling you that, either they're just sincerely indoctrinated and they don't know the literature, or they do know the literature and they're intentionally deceiving you. Though one of those two things is probably true. Okay. Because there's so much overwhelming information and evidence to refute this whole balanced plant nutrient nonsense that it's laughable at this point. It's asinine to even consider it. But we'll get to it. And there's a paragraph down in here later where he makes a claim, or not a claim. He just says it with such presupposition that it gets into the literature, and then you can read it and go, well, if you're unfamiliar with it, then you can read that and believe it's true. And I'll get to that here. It's sort of towards the end of the paper. The purpose of this study was to determine the effects of 5 nitrogen sources, 2 potassium sources, and 3 potassium rates on soil nutrient levels and the growth and elemental composition of pin cross creeping bentgrass. Now, he's going to show a lot of tissue analysis in this paper. I'm going to show a little bit of that just because I think it's important, particularly with sodium. But beyond that, I'm not overly interested or concerned about tissue analyses in terms of its practical application or importance to you all. Okay. It's important to me and scientists to kind of figure out what's going on and all that stuff. Occasionally it can be used and applied in the real setting, but not that much. And so I'm not going to go into a great deal of detail on the elemental composition of these nutrients. The experimental area consisted of 6-year-old stand of pen-cross creeping bentgrass maintained under putting green management. The turf was established on a Hagerstown silt loam and a mixture of sand, Hagerstown soil, and peat. And remember, this is pre-USGA spec greens. This is in the 70s, early 70s. So today's USGA construction of putting greens, that's commonplace, didn't exist to the same extent back then. In this experiment, 5 nitrogen treatments represented a continuation of previously applied nitrogen sources on the 2.7 by 7.3 meter plots. Treatments were urea. So he also has nitrogen in here. And I'll go into a little bit on nitrogen, but I'm more interested in the potassium for this episode. Treatments were urea, argonite, which was a 700, process tankage, which the argonite is a process tankage. It's like a natural organic byproduct of treatment. Okay. Still around today with more ag stuff. Milorganite, which is activated sewage sludge, and 2 sources of urea form, which are uramite and nitroform. So we're going to be looking at urea and process tankage and milorganite and so forth and nitroform. Urea was applied every 2 weeks. And 12 or 13 equal applications per season, and the natural organics were applied every 4 weeks, which was 6 or 7 applications per season. I think that means per year. I guess it could be per season. Yeah, per season. 12 weeks. Yeah, per season. Okay, total nitrogen applied 1966 through 1969 was, and he has these things he has these units in R's. It's driving me nuts. But anyway, the total nitrogen applied in 1966 through 1969 was, say, 7 pounds of nitrogen. Well, around 7.5 pounds of nitrogen. Oh, well, there we go. He transferred it into English. So 7, 8, 8, and 6.5 pounds of nitrogen per 1,000 square feet in 66, 67, 68, and 69. So around 8 pounds per year in each year. In 1966, nitrogen plots were split for potassium treatments. And 2 and 4 pounds of potassium. Oh, he has it. 0, 2.5, and 5 pounds of potassium per 1,000 square feet were applied to those split plots. Subplot size, and then he has the subplot size. The source of potassium was potassium chloride, and the amount of applied was split equally between the spring and fall applications, which corresponded to the dates of the urea-form applications. So he used potassium chloride, which is good if you want to confirm the response was from potassium. So he used that. And so we're going to see positive responses to this. I wouldn't be overly confident with these results, but they do show some positive responses to potassium chloride nonetheless. So it is, it's there in the literature, but I'll get to it in a second. Like the manner in which the data are reported are a little bit ambiguous. You can't really pull out all the little details. And so just be careful if you ever choose to use this as a good reason to do something. I would just be real careful with this particular paper because there's many other papers that are a little bit more detailed, I guess. Portions of the clipping was retained for elemental analysis. Available soil nutrients were determined using a neutral normal ammonium acetate extraction for potassium, calcium, and magnesium, and Bray 1 was used for phosphorus. So all normal stuff there. Then there was a second experiment. In this experiment, 2 potassium sources were applied at 3 rates in a single and split application. Potassium chloride was included as a source of soluble K, and fritted potash served as a source of slow-release K. Fritted potash is produced by fusing feldspar and potassium carbonate. Okay, main plots were treated with either a single spring or a split spring fall application of fritted potash or potassium chloride. The plots were split with 3 levels of potassium. What were the rates? 0, 2.5, and 5 pounds of K. Is that what it was? Yeah, 0, 2.5, and 5 pounds of K. Clipping yields, elemental analysis of clippings, and soil analysis were determined using the same procedures as in experiment 1. So that's the materials and methods. So the short and skinny of it is they have 2 experiments. One of them, they have a couple different nitrogen sources and a couple different potassium sources. They have different nitrogen rates. And, they have different, it's split up. The nitrogen was applied, split up throughout the season, and the potassium was applied, I'm sorry, let me back up. The nitrogen was roughly applied around 8 pounds per 1,000 square feet per year. The potassium was applied at 0, 2.5, and 5 pounds. Okay, so they're increasing the rate of potassium in the first experiment, or they're basically keeping the nitrogen the same. But the source was KCl in the first experiment. And then the second experiment, they looked at fritted potash and KCl, and they increased the rates from 0, 2.5, and 5 pounds of K. And they're applying this to creeping bentgrass. I see they don't say where. That's what I'm saying. I'm pretty sure this was in Pennsylvania, because this Hagerstown silt loam is common in that area. And it says this was a contribution from the Pennsylvania Agricultural Experiment Station, so I'm pretty sure it was conducted at Penn State. But because this was so old, the standards for publication were just less back then. And so that's one reason why I wouldn't have as much confidence as in this paper as I would in the newer papers, because there just wasn't quite as strict back then. And so some of the information that you would look for as you would assume would just be common in today's literature wasn't in this paper. And that's not a knock on this paper. That was common to most papers back in this time period. Okay, so the results and discussion. Experiment 1. Soil nutrients. Soil test results for phosphorus, potassium, magnesium, and calcium are shown in Table 1. Phosphorus and magnesium levels for malorganite plots were significantly greater than for other nitrogen sources. These results would be expected because the phosphorus and magnesium, about 1%, contain a malorganite. I've mentioned this many times before, okay? If you're going to apply malorganite or any other natural organic that has phosphorus in it to a turfgrass that is not deficient in phosphorus, you are going to inflate the soil phosphorus level unnecessarily. And there's at least one paper I know of, probably more than that one paper, that clearly conclude that as the soil phosphorus level increases, so too does the risk of phosphorus runoff. Not phosphorus leaching per se. Phosphorus is generally going to stay where it is in the soil in terms of vertical movement. But the runoff risk of phosphorus increases greatly as the soil phosphorus level increases as well. So this concept or this idea in the industry, particularly in the lawn care industry, it does happen in golf too. And it does happen in sod production as well, where we're applying these natural organics because they're only $300 a ton or whatever. And we're going to increase our carbon or whatever the other, perceived benefit is. You're going to create a high level of phosphorus in that soil if you do it regularly over many years. Okay. Unnecessarily. That's the key. You're applying phosphorus unnecessarily. And that's what they found in this paper right here too. It's set in the 70s, for goodness sake. Phosphorus levels were greater from malorganite than the other nitrogen sources. Potassium rates significantly influenced potassium, magnesium, and calcium levels, but the differences were only slight in the cases of magnesium and calcium. Potassium was greater and magnesium was lower with the 5-pound potassium treatment than with the 1 or 0-pound potassium treatments. So what that says is real simple. The application of potassium at 5 pounds reduced the concentration of magnesium in the plant tissue. They're saying it was probably of no consequence, which I would agree. It's probably not going to cause any harm. But you're still going to alter the plant uptake of cations when you're applying potassium. In some cases, that could be favorable, which I'm going to go over right now, or here in the next couple sentences, or whenever I get to the table. And I'll explain that when I get to it. I even highlighted it so I wouldn't forget it. Okay? But in most cases, the reduction of the application of potassium is going to reduce other cations, usually in the tissue, calcium, magnesium, and so forth. Again, I wouldn't get overly concerned about that per se, because generally the plant's still going to have more than enough calcium, magnesium. It's all over the place. But just be aware that you're altering the uptake of cations in the plant tissue by applying potassium. Be aware of that. So, because if there is no benefit to applying potassium, then understand that only one of two things could occur if there's no benefit: either no response or a negative response. Okay, and here's kind of sometimes what can happen. You can reduce the cations in in the plant tissue. Again, I wouldn't worry too much about that right now, but it could happen. Calcium was higher at 0 potassium than at the 2.5 or 5 pounds of potassium. So it was 2.5 and 5 pounds of potassium. Reduce the calcium in the tissue. And then what he says here is where what I mentioned in the introduction is that the next sentence says, balance is important in determining the availability of these cations to plants. It is not important. Okay? Make sure that's clear. I'm saying this in this paragraph as the author quoted it. But understand, even the investigator, the researcher who's responsible for the base cation saturation ratio theory, in the same year, 1945, I think it was, end of World War II, in the same year he published the article saying that cations should be balanced, he also published another paper that said, well, as long as there's enough in the soil, the balance is unimportant. In the exact same year, from the exact same author. Okay? Berman Bear. So even the author that started all this nonsense has clearly, in the same year, said it's not that important. As long as you got enough, you're fine. But it's continued to perpetuate and to continue to grow. And even in the literature here in the 70s, so this is, 15 years after the concept was introduced, it gets into the literature and is stated in such a factual way when in fact it's not factual. So nevertheless, he says balance is important. The percentage saturation in a balanced soil will generally fall within these ranges. And then he has potassium 2 to 5, magnesium 10 to 15, calcium 60 to 80. And then he cites this paper, 6, and I'm sure that's the Berman Bear 45 paper. Oh no, this is a different one, interpreting soil tests for turfgrass maintenance. So this is just an internal Penn State leaflet, basically. So that's even worse. The 0, 2, and 5 pounds of potassium treatments had potassium saturations of 1.7, 1.9, and 4% respectively. Magnesium saturation range from 18 to 19%, and calcium from 77 to 79%. So what he's saying basically is that the application of potassium in this study altered the base cation saturation in the soil. Okay? Completely useless. Forget about it. I think if I tried hard, I think I could actually go over a paper a different paper every week for an entire year. And every paper will refute base cation saturation. I bet there's 50 papers in the literature that will clearly show the calcium magnesium ratio is useless. Base cation saturation is useless compared to just sufficiency levels. I bet I could do that. That's how strong the evidence is refuting base cation saturation. So don't believe it. And I'm sorry he put it in here. I marked it in red. But I just wanted to point this out, that it is occasionally in the literature, especially in some of the older literature, where even in those days, even in the early 1900s, before Berman Bear even posted that, there was clearly literature refuting this stuff. But nevertheless, it's in this literature as if it's fact, when in fact it's not fact at all. Don't believe it. Under most conditions, it would be expected that phosphorus and calcium levels would be greater near the surface because of the immobility of these elements in the soil. However, on these plots, significantly higher levels of phosphorus and calcium occurred at the lower sampling depths. Now, he has sampling depth differences in this paper, which I'm not going to go into a great deal. But he didn't find that the 0 to 5 or 0 to, I guess it was 2 inch. I don't know what the depth was. 0 to 2 inches. He didn't find greater nutrients in that 0 to 2 inch as he did in previous papers. There's previous papers that show the nutrient levels tend to stay elevated towards the surface of the soil. And he didn't really find that. And he kind of postulates as to why that might occur. If you want to read about that, you can download the article and read about it. I'm not going to go over it. Potassium content tended to increase, and calcium and magnesium tended to decrease with time and the plots receiving potassium fertilization. Okay? So basically, over time, Potassium went up in the soil and calcium, magnesium went down in the soil. Okay. From the data on elemental analysis, tables 2 and table 3, the following observations can be made. See, that's what I'm saying. I don't mean to be like picky, but it's like we don't use that language nowadays. It would never be allowed in the literature today, saying tended to do this and the observations can be made. You either conclude it or you don't conclude it, whatever the results were. So that's what I'm saying. Be real careful about taking too much of this information and using it. I need to go over this paper at some point, and this is the best place to put it, I guess. Nitrogen content was greatest with urea in the tissue, except in the spring period. Okay. Nitrogen content was highest with no potassium fertilization. So if you want to mark it down as a negative, I don't know if it's a negative or not, but as potassium increased, the nitrogen content in the tissue decreased. The greatest nitrogen in the tissue was found at the lowest potassium level, no potassium. I wouldn't put too much into that, but it's there. Calcium and magnesium contents decreased with increased potassium fertilization. Although significant differences in elemental content occurred with the majority of elements and some of the trace elements, no levels seem to be critically low. So in other words, it decreased, but it probably wasn't that important. And I would agree. I mean, you have to really screw up some stuff in the tissue, like really do some crazy stuff to get the tissue levels of the calcium, magnesium low enough to actually see a deficiency or a problem with it. But nevertheless, it will alter it usually. Growth and color. Clipping weights were significantly affected by both nitrogen source and potassium rate. So here's where I have to include this paper in the positive column, because he says right here, clipping weights were affected by potassium rate. All right. And that's when I was reading this, I'm like, well, that's a bit curious, and he used KCl. So, I have to just like, okay, well, read more. It seems a little bit odd. You'd see that, but that's what he found. So I keep reading it. Let's just keep reading this and I'll go back to the table because it's kind of funny. Okay, here we go. Ureaform and urea usually out-yielded the natural organics, and milorganite out-yielded agronite, though through the months of June. So ureaform and urea outperforms milorganite and natural organics. Where have we heard that before? Yields were similar in July, but during August and September, the growth with milorganite was greatest with a few exceptions. Oh, there you go. Milorganite turned up on the end, towards the end. Yields from agronite, this was the process tankage. I think that's what that was. Yields from agronite plots were usually low, but they out-yielded the others on 2 August dates. So occasionally it was greater, so occasionally it wasn't. The greatest increase in yield due to potassium fertilization was between no potassium and 2.5 pounds, rather than from 2 to 5 pounds. So if you applied a little bit of potassium, they saw an increase. And we'll see that with the influence on winter kill as well. We'll see that with influence when we get to warm season grasses when there's a benefit. The greatest benefit is from 0 to just the smallest level, just any potassium. You don't need to apply 5 pounds, 7 pounds, 9 pounds of potassium. When you're going to see a turfgrass response to potassium, which is extremely rare, but when you're going to, it usually comes with just a little bit of potassium, not a lot. Okay? So I was reading this, and I was like, well, dang. I mean, he found a response, no problem. I mean, it is what it is. It's an older paper, no problem with that. The way it was done is a little bit odd, but okay, he saw a response. And okay, he saw a clipping yield response. And I thought it was a little bit odd. And I was like, but it happens. It's not common, but if the potassium is that low, then, it's possible you'll see a response to any element if it's so low that it's restricting its growth, right? And in this case, apparently it was that low. But I was reading through here, and then in the next paragraph, and I'm going to try to read this paragraph without laughing, but it's hard, okay? I'm just letting you know it's not easy, okay? Color response to potassium applications was noticed the first season and became more prominent in the following years. And I'm like, damn. So they saw the clipping weight response, and now they're saying a color response. And I'm like, that is strange. I was blown away when I read that sentence. I'm like, this doesn't make much sense, but whatever. So then I read the next sentence. Plots receiving no potassium had darker foliage than those that were fertilized with potassium. I mean, how many times have we seen this? So the literature since then has continued to convince me that potassium applications generally won't result in any response, much less a quality response. And even in the 70s, when they say a color response occurred, I'm like, how in the world is a color response occurred? And then he says right here, the color response was actually a harmful response because no potassium was, the turf with no potassium was the darkest green. I love that. Oh, Lord. The only striking difference that occurred in color of nitrogen treatments was consistently lighter green color of milorganite plots. So again, milorganite's getting beat up. The lighter green color from milorganite. They got to apply milorganite. We got to throw her down. I mean, if you do it at the right rate, at the right time, I've said before, you can do it with any nitrogen source. But consistently in the literature, you'll find that turfgrass, if you're comparing nitrogen sources, turfgrass under milorganite treatments generally will not be as high quality or color than from, say, urea or something along those lines. Okay, the difference was slight. Then it says, another observation has been that the plots receiving no potassium exhibited earlier greening and growth in the spring. Oh, God. Oh, man. So I'm reading this paper and I'm going, man, something's wrong. I mean, this is totally against what I know. This is totally against what I'm aware of in the literature. And then, no, it's not. He's saying there's a difference, but the difference is that potassium reduced the quality. Potassium reduced the greening and the growth in the spring, the application of it. And here we are applying fertilizers in the fall, and we're coming out in fertilizers in the springs because we want that early spring green up. We want to be the first to green up, and it's really important. We got to get that extra week in the spring, and it's super important. And you're applying it with potassium on this bentgrass at least, thinking you're going to increase the spring greening and the growth in the spring. And in fact, the potassium is resulting in the opposite effect, at least in this paper. It's ridiculous. I mean, that's the reason I said at the beginning, I want to know how we got to this point. How do we get to the point where potassium has to be applied? Potassium is a stress element. We got to apply it. We got to reduce the stress. We got to reduce disease. We got to reduce all this stuff. And I mean, and most of the time, it's either nothing or a detrimental effect. I'm telling you. It's absurd. God. Can you imagine the millions and millions of dollars that have been wasted applying potassium because people think it's going to be beneficial to their turf? It's absurd. Okay, so let's look at these tables here real quick before I go on to this experiment 2 results. And what I'm looking at here, table 2, is the effect of nitrogen source potassium rate in year on NPK, calcium, magnesium contents of pencross creeping bentgrass. And then in the next couple ones down, it's going to be basically the same thing, but it's going to be in a different year. So this is the first one's clippings for 3 seasonal sampling times, and the next one's going to be in 1968 only. So I can't really zoom into this, but I'll do my best to read it. What we're looking at here is the potassium rate of either 0, 2.5, or 5 pounds of potassium. And we're looking at the nitrogen content. So you're going to want to look from left to right if you're reading this. So when we applied no potassium, the potassium or the nitrogen content was around 5.1. Yeah, see, they don't even have the unit, but I'm sure it's percentage or grams per kilogram. Yes. Oh, here, elemental percentage over here on the left. So yeah, elemental percentage. So 5.1% when no potassium was applied and 5.0% when 5 pounds of potassium was applied. And they claimed that was a significant difference. I would argue as the authors argued, it's probably insignificant in terms of any practical importance. But they showed a reduction in nitrogen, applying 5 pounds a K. And then, of course, when you apply potassium, the potassium is going to go up. It went from 1.7 to 2.7. So the potassium in the tissue went up. Yay, hooray, for whatever reason you'd want that to happen. I mean, the turf quality went down. but the potassium in the tissue goes up. So you'll have the potassium in tissue go up pretty much every time. Again, as I've said before, I don't particularly care about that unless there's a strong correlation between that and some other metric that I'm interested in. And there will be with some winter kill issues. I think there might be even some with anthracnose, if I'm not mistaken, where you want to stay above a certain percentage. You can at least use that to help diagnose problems. But for the most part, potassium in the tissue, I mean, it's nice to know, but I wouldn't use it for any fertility management practices unless you have some more information, basically. But here's where they were talking about, the authors were talking about reductions in calcium and magnesium. Calcium went from 0.7% to 0.5, and that was significant. And the magnesium went from 0.3 to 0.2, and this was in the spring of over the three. I thought that was in the year, but that was in the spring. And you basically see the same thing in the following years, or the following seasons, in the summer and the fall. You'll see potassium goes up as potassium is applied. You'll see nitrogen goes down as potassium is applied, and calcium, magnesium go down as potassium is applied. Okay. But I do want to go down into the 1968 season because this isn't always necessarily a bad thing. The same thing occurs with nitrogen, potassium, and calcium, magnesium in 1968 growing season. Okay. Where you see nitrogen go down as potassium is applied from 0 to 5 pounds. Potassium go up, calcium, magnesium go down. Same thing as we've documented before. But this isn't always a bad thing. You see manganese go down as well. When you look down here, these authors also measured sodium. And sodium in the tissue with no potassium was around 300. That would be parts per, okay, yeah, it's over here. 300 parts per million. When you apply potassium at 2.5 pounds, that 300 declined to 80. And then when you applied 5 pounds, it declined to about 70. So you do see a decline in the leaf tissue of an element, in this case sodium, that we might desire. If you have high sodium in your irrigation water, or you just are plagued with sodic soils or high sodium in your soils to the point where it's actually harming your turf, or your turf grass is unacceptable because of some sodium source. The concept has been around for ages of, well, you can apply potassium and it'll help alleviate some sodium issues. And as early as the 70s, they concluded or documented that indeed the sodium in the tissue will very likely decline when in the presence of potassium applications. So you're reducing the sodium to a very, reasonable level, 300 down to 70 by applying potassium. Okay. And that's pretty consistent in the literature as well. All right. I thought there was another one. No, there's not. But this was one of the earlier papers I can remember, I can recall that showed this reduction in sodium following the application of potassium. Okay. So, and I got that question either on a live stream or on an email. I don't remember where. And I don't remember exactly how I even answered it, but I would say that there are good reasons to apply potassium when your turf grass is unacceptable as a result of sodium. Now, you have to diagnose that. It may be unacceptable for some other reason. But if it is unacceptable as a result of sodium, then the application of potassium can help. Okay? Now let's go to where some of the stuff gets a little odd here, where they talk about frequency of significant differences in fresh clipping weights. And this is how they showed results in the past. They just showed like the number of occurrences, like the p-value was less than 0.05. And they did 21 sampling. Sometimes I kind of like this, but they did 21 samplings in 1966. 17 times the nitrogen source mattered. 9 times the K rate mattered. And then 17 samplings in 1967. Of those 17, 13 times the nitrogen source mattered, and 11 times the K rate mattered on clipping yields. So, and you'll see it's pretty consistent from 66 to 69, where nitrogen source and K rate mattered on clipping yield. But what they don't do is they don't provide the exact increase in terms of mass. They do show, you can infer that from over, you don't have to infer, you can actually see it over here a little bit, where they provide the data in a very peculiar way, where the average relative fresh clipping yields relative to 0 potassium, and it says 0 potassium would be set at 100, and then the potassium rate goes to 2.5 pounds and 5.5 pounds. You see the clipping yields go up to 113. So that means it went up 13% when it was 2.5 pounds a K, and it went up 23% when it was 5 pounds a K. Now they're going to conclude at the end that potassium really didn't have much of a meaningful effect on any of this stuff. But they do show, and this is the reason why I have to include it in the positive column, they do show an increase, but I don't know how to interpret that, because later on they conclude that there really wasn't much happening. So take it for what it is. Experiment 2, which is where we had 2 different potassium sources. The effect of potassium applications on exchangeable potassium is affected by the potassium fixation and release characteristics of the soil, and different results could occur with different soil types. The reason I highlighted that in yellow is because we've been talking about potassium mineralization from potassium-bearing minerals. We have not talked about fixation of potassium in certain types of clays. But with potassium, these authors actually noted here that the mineralization or release of potassium into the soil solution can occur in some soils, and the opposite can occur, where the soil can actually absorb it out of soil solution depending on the minerals that are in the soil. So, and the soil test extractant, let's just pick Mehlich 3, isn't particularly good at extracting a portion of that potassium that's in the actual mineral itself. So you could extract a portion of potassium out of the soil. If it happened to be a soil that was high in potassium-bearing minerals, let's say you had 15 parts per million on your Mehlich 3, but it's not accounting for the potassium that's going to be mineralized out of that potassium-bearing mineral. It's not accounting for that, because the soil test extracting the Mehlich 3 isn't going to really pull much of that out. So you get a soil test that says 15 parts per million potassium. Well, let's say 15. Let's say 30. It says 30 parts per million potassium. And you go, oh, I'm low, I need to apply potassium. But you don't realize that the soil itself is providing some potassium that the test didn't account for. So you might not actually need to apply any potassium. Or the reverse could happen, where the soil is actually absorbing potassium out, where the potassium, say, is 30 parts per million Mehlich 3. And you go, oh, well, I probably need to apply some. Well, you might need to apply some, but it might be actually worse. Let's say the potassium level was 50 parts per million, where you might say, I probably don't need to apply any. But the soil's pulling some of that out of the solution, and the soil test isn't going to account for that. That 50 parts per million might be low in those types of soils. So there's a lot going on with potassium in the soils, is my point, to where soil tests will kind of give you a ballpark idea, but you can't just pick a number. You can't just say it's going to be, you should be greater than 60 parts per million. You should be greater than 30 parts per million. Okay. It's probably somewhere in the 30 to 50 parts per million range, but it's going to depend on the soil. And that's what they say in 1972 in this paper. Okay. Fixation and release characteristics of the soil, and different results could occur with different soil types. And I completely agree. Different soil types will have a different impact on potassium availability or solubility. And soil tests generally will not be able to account for that influence. Okay, we're getting close to the end, only a couple more paragraphs. Significant differences due to K rate, potassium rate, occurred with potassium, calcium, manganese, and sodium in both years, with phosphorus in 1966 and with magnesium and nitrogen in 1968. The increase in potassium and copper content and decrease in sodium, calcium, magnesium, manganese, and sodium due to the increases in potassium fertilization are in agreement with the results of experiment 1. So they found the same thing. Applying potassium is going to alter the cations in the soil. Basically that simple. Mass action. You're throwing a bunch of potassium out there, and it's going to knock off cations that are on the soil. Either they're going to leach through, or they're going to be immobilized, or something else is going to happen to those cations. Maybe they get taken up. But the application of calcium is going to alter, or any cation is going to alter the other cations that are in the soil. And it might very well alter the cations that are in the tissue, which is what this paper showed. There's no need for that unless you actually need the potassium. Okay, if you need the potassium, that is what it is. But if you don't need the potassium, why try to go screw up something that's already working, you know? Although soil levels and plant uptake for some elements were decreased by potassium applications, the magnitude of these changes was not considered critical. And it's probably true. I mean, you're altering the amounts that are in there, but it's probably irrelevant, to be honest. In some cases, it is relevant, such as sodium, where you might actually want to reduce sodium in the tissue. But the chances of you reducing calcium so low that you'd have a deficiency is remote. Okay? You'd have to really screw something up to get calcium and magnesium so low that the turfgrass is going to be unacceptable as a result of that. Okay? But nevertheless, be aware that you are altering things. Growth and color. Fresh weights of clippings were affected by potassium source and rate on some occasions. Occurrence of significance due to treatments is shown in Table 8. I think, I didn't show that. Potassium source significantly influenced yield on 16 of the sampling dates. So 84% of the time didn't do anything. 16 of the times potassium source did affect it. With one exception, the difference resulted from higher yields with potassium chloride application. So only with one exception. There was higher yields with KCl than with the fritted potassium. Yields were significantly increased by potassium on 21% of the sampling dates. At times, a significant potassium source times potassium rate interaction occurred due to higher yields with increasing KCl, but not to fritted. In other words, the yield sometimes influenced when KCl was applied, but did not change when fritted potash was applied, and that's what created the interaction. So KCl is soluble, fritted potash is not as soluble, and there wasn't much of a response to the fritted potash. The KCl actually resulted in an increase in yield, which is not that common, but on low K soils, I suppose it can happen. Color differences due to potassium source were not noted. Again, as in experiment 1, a darker green color was observed on plots that received no potassium. So we got, since 1972, guys and gals, we have clear evidence in the literature that the color, at least of this creeping bentgrass, may be reduced as a result of applying 2 or 5 pounds of potassium per year. Just leave it alone, the turf would be greener in this setting. Okay, the clipping yield went up with KCl, which I don't know necessarily if you'd want that in all cases. You probably don't want clipping yields to go up that much. But clipping yield was influenced. If you want to say increasing clipping yield was a benefit, then I'll put it in the benefit column. But the color was harmed, reduced. So it's got to go in the negative column too. The lack, and here's where the conclusion, even though there were some differences and there were some increases in growth rate, they conclude at the end here, and this is where I struggle with this, the lack of major differences in growth, chemical composition, and soil test values due to K source and application frequency under the conditions of this experiment suggests that the main advantage of fritted potash would be decreased burn hazard. So there would be no value to fritted potash unless you just want to reduce the burn. So there wasn't much value to potassium other than to yield. So if you want to increase the yield on creeping bentgrass, I suppose KCl might do that if the potassium is very low. And remember, the potassium in this study was determined through ammonium acetate. And the ammonium, where did I get that from? The ammonium, right here, the ammonium acetate. Let me pull this up right here. The ammonium acetate at the 0 to 5 or the 0 to 2 inch depth with no potassium was 0.16. That's milliequivalents per 100 grams. So somewhere in here, let me see if I can find it real quick. I thought I had that on here. Well, I found it in here somewhere and I already put it on the PDF. Make sure I'm right. Make sure I'm right here. 15, I had it at 15 parts per million ammonium acetate, but can't seem to find it now in the. Oh, here it is. Oh no. Huh. I'm gonna have to delete that because I got it wrong on that one. But let me remove that because I don't know what it was. They had it in milliequivalents. I'm gonna put a question mark on that. Milliequivalents aren't exactly what I'm looking for on that. So the short and skinny of this paper is they did some nitrogen potassium work in, I believe, Pennsylvania, even though they didn't state it exactly. And they determined that the application of potassium at 0, 2, or 5 pounds of potassium per year actually did have an influence. It increased clipping yields, but decreased turfgrass quality. The potassium source KCl generally any result that did occur in terms of clipping yields resulted from KCl, not the fritted potash. Okay. That's the take-home message of this paper, guys and gals. So it goes both in the negative column and in the positive column. So let me put that on screen here. So I'm going to put this, which is Waddington 1972. So I'm going to put Waddington et al. 1972 in the positive column because it was yield, and I'll put yield. Okay. So that it wasn't quality, it was yield. And then most of the time nothing happened, which is I'll put it in nothing. And then there was a negative response to quality. So this fits all of them. So we have now 2 articles in the positive column. Both of them were a yield response. Oops. And we have 4 articles in the negative column and 4 articles in the nothing column. Okay. So we have yet to actually document a positive response to turfgrass quality following potassium applications. And we've gone through 4 papers on Kentucky bluegrass, perennial ryegrass, and creeping bentgrass. That's going to change when we get to warm season grasses, because I know there's a couple papers that actually do show a positive response to a turfgrass response to a quality response to potassium. So we're going to have a couple over here in the positive, but it's not very good. And these aren't equally weighted. In other words, like the amount of responses that we found as none in these articles was substantial. Remember, the yield was, I think it was like 20% of the time you saw a yield response. 80% of the time, there was nothing happen, okay, in terms of yield. So even when there was a beneficial response in the Waddington paper, it was only like 20% of the time, 25% of the time. So all the other time, there was nothing happening. So it's not equally weighted, but nevertheless, that's the way I'm going to keep the scoreboard going. Okay, guys. I'm going to read some chat, and then I'm going to close this thing off. So Randy from Bulgaria says, any basic thoughts why I get best color longevity from calcium nitrate compared to ammonium nitrate and ammonium sulfate? Same rate of nitrogen in high pH native soil. How would you approach such a case? Well, I mean, you just want to know my thoughts on it. My thoughts are that I don't know what the high pH soil is. I don't know, what high pH means to you. But if I'm in a high pH soil, well, it depends on what the pH is. But if you're seeing a better response from calcium nitrate, I would want to confirm that that's actually true. In other words, you may be seeing a better response from calcium nitrate, or you may not. Observations are very dangerous. They're very convincing. That's the reason they're very dangerous, because it might not be true. But you can get good turf from any soluble nitrogen source, basically, as long as you put it at the right rate and the right timing. there's nothing wrong necessarily with calcium nitrate. It's an extremely expensive way to do it, but it has nitrate in it. You'll see a positive response to that, as you will from ammonium nitrate, as you will from ammonium sulfate, as you will from potassium nitrate. You'll see a response to those very well. So if your pH is 8, Randy, and you're applying calcium nitrate, I would ask why. I don't know why you would be applying calcium nitrate at a pH of 8. But it's not surprising to me that you'd see a turfgrass response to calcium nitrate. No. But your question has a lot more to it than you might expect, and that is, you're convinced that you see a better response from calcium nitrate based on your experience, and it might be true. You very well could be true. But before I start going down the roads of trying to figure out what's going on, how is this happening, I would want to actually confirm that that's actually what you're seeing. So a perfect example is, in the last year or two, the sulfur work that I was doing, I just was not convinced that the response could possibly be due to sulfate. Could not believe it. In fact, I was sitting at the on the plots with the saw producers saying, this shouldn't happen. This should not happen. Okay. It's very unlikely that this is actually happening. Even then, when I put it out myself and I saw a response, I'm like, I don't think that that's actually what's going on. But I was wrong. I mean, it was sulfate. The point is, you have to do a lot more work to actually diagnose. Indeed, it is a better response from calcium nitrate than ammonium sulfate or ammonium nitrate. There's a lot more work that needs to be done in sort of pilot studies. So I did a pilot study in that case, and I just did, magnesium sulfate, calcium sulfate, ammonium sulfate, urea. I just wanted to make sure that I'm doing what I can before I jump in and do a full study. I just did 3 or 4 plots. It's not really a pilot study, but I do that as I'll identify that as a pilot study, just to kind of get a general idea as to what's going on before I really jump in with both feet and start investigating it. And in that pilot study, I saw no response from urea. I saw a response from magnesium sulfate and calcium sulfate and ammonium sulfate and potassium sulfate, whatever the other one was. And I'm like, you're not going to see a response from potassium sulfate. You're not going to see that. But I did. And so that's what started me down that road. So I guess what I'm saying is I do a little bit more. Maybe you have. I don't know what you're doing and not doing, but I would be a little careful about assuming that it's true until you have a little bit more information. And maybe you do have information. Like I said, I don't know. I don't know what you've done or haven't done. All right, guys, I'll be back tomorrow morning with another potassium paper. I'm going to leave you with some more music today. And don't forget, if you want to do Calendly, sign up. The prices on the Calendly are going to go up in April. So this is the last month. If you want to consult with me at that set fee, this is the last month for that. And next month, the memberships are going to open up and the Calendly prices will go up, but not for members of the channel. It'll stay at the $50 for all members of the channel. Okay. So Randy, send me an email or we can chat about it more later about your work. Okay, guys? Thanks. Appreciate it. Talk to you guys tomorrow. Bye.